is to go over kinematic equations and the motion of particles. And what I mean by kinematic equations is the equations that we use a lot of the times, which is our velocity is equal to initial velocity plus acceleration times time. My position is equal to an initial position plus an initial velocity times time plus 1/2 times my acceleration times time squared. And we have a third one, which is my velocity squared is equal to my initial velocity squared plus 2 times my acceleration times x, which is my position, minus an initial position. So the first thing I want to do is I want to go through and I want to derive these equations and show you where they come from and the limitations we have on these equations. So it's really important that we know when we can use these equations and we know when we are not allowed to use these equations. So first of all, where do these equations come from? If I just call this equation 1, this equation 2, and this equation 3, what I want to do first is I want to derive equation 1. And to derive equation 1, I'm going to go back to the equation I have that my acceleration is going to be equal to the change in velocity dv over dt. And what I want to do is, just like we did before, is separate this and integrate. So I'll have my acceleration times time is equal to dv. And I said I want to integrate. And I did a bunch of examples last week. And with these examples, we would have an expression for acceleration. So acceleration would be something like 4t squared plus t plus 1, something like that. We would plug it in, then we would integrate it. But to get these equations, these are a special case where what we're actually going to say is acceleration is constant. So that means acceleration cannot be a function of time, it cannot be a function of velocity, and it cannot be a function of position. So I would just have to have acceleration is equal to some number, say 9.81, which is gravity in SI units. So when my acceleration is constant, what that allows me to do is it allows me to take this acceleration and bring it outside of the integral. So when I bring that acceleration outside of the integral, I'll have my acceleration times the integral of dt is equal to the integral of dv. And we're going to have to figure out our bounds of integration. So we're going to go from some initial velocity to some final velocity, and we're going to go from some initial time, and we usually say our initial time is time 0, so t is equal to 0, to some unknown time. We don't know whatever time we're interested in. So when I do this integral now, I'm just going to get that this is going to be a times t, which is evaluated from t to 0, and this is equal to v, which is evaluated from v to an initial velocity. And right, our initial velocity, we could be moving with an initial velocity of something. It doesn't need to be 0, which is why this isn't just equal to 0. So now when I plug our initial terms in, I'll get that my acceleration times time is equal to v minus our initial velocity. If I solve for v, I'll get v is equal to my initial velocity plus my acceleration times time. And this right here is my equation 1. So the limitations on these equations is that my acceleration must be constant. If my acceleration is not constant, I cannot use the kinematic equations. And this is a problem that when I was teaching this class, I would see a lot. If there was accelerations equal to a function of something, you can't just force it into these equations, because these equations come from the assumption that we can bring up the acceleration outside of the integral. If you do have an acceleration that's not constant, you would have to go back to what we did last week and just put the acceleration in here at this point, take the integral, and solve the equation that way. But this week, we're dealing with a special case. All right, so now let's look at equation 2. We're going to be doing the same thing. So with equation 2, the base equation we're going to be using is that my velocity is going to be equal to dx dt. And we have a special form of what my velocity is. My velocity, we're going to use what we found from equation 1. So my velocity is going to be equal to v naught, my initial velocity, plus a t. So if I put that into this equation, v naught plus a t is equal to dx dt. And what I want to do is I want to separate and integrate. So if I separate and integrate, I'll have that v naught plus at times dt is equal to dx. And let's figure out the bounds of integration. Now, right, I can't bring acceleration out right here. But this the acceleration is constant is still a requirement. So what I'll have is that this is going to be time. So this time is going to go again from 0 to some time t. This is going to go some initial position x naught to a final position x, or you might see it as x of f in some cases, depending on the book you're using. So now I just want to take this integral. And when I take this integral right here, I'll have this is my initial velocity times t, plus this term is 1/2 a t at squared. And this side is going to be x, and this is evaluated from x to x 0, x naught. I already applied on this side. I already did the bounds because 0, both the terms just go away. So when I do the right side, what I'll get is, well, this side, v naught t plus 1/2 at squared is going to be equal to x minus x naught. If I rewrite this in terms of x, I'll get that x is equal to x naught plus v naught t plus 1/2 a t squared, and this should be what we have for equation 2. So then finally, we want to get our third equation. So equation 3, what we're going to do is we're going to use the other form of what we have for acceleration. Acceleration is going to be equal to v dv over dx. Again, we can separate and we can integrate. So when we separate this, we're going to get a dx is equal to v dv. We're going to integrate. In this case, a can come outside our bounds of integration. It's by itself. Oops. So I'll just put it right here. And this is going to go from x, initial x to a final x. This is going to go from an initial velocity to a final velocity. And when we integrate, we have that this is going to be a evaluated from x to x, a times x, which is evaluated from x to x0, is equal to, well, this v right here is going to be v squared over 2. This is going to be evaluated from a final velocity to an initial velocity. So if we do this, we'll get a of x minus a x initial x is equal to vf squared over 2 minus v naught squared over 2. Well, here we can just say, all right, this is a of x minus my initial x. If we multiply both sides by 2, we get a 2 right here. And so this is going to be equal to vf squared minus v naught squared, right? So now if we solve for vf, we'll get that my vf, or in this case, I had a final velocity was just v, but vf squared is equal to, this goes to the other side, so v naught squared plus 2 a x minus x naught. And that's the third equation that we had. So that's where all three of these equations come from. And again, the limitation of using these equations is that our acceleration must be constant. If our acceleration is not constant, we need to go through the actual integration on the problem. So these are the type of the type of equations and the type of problems that you would see in a beginning physics class or maybe a high school physics class. And we're just going to go over a couple of these. So with the first problem, what we have is that a motorist enters a freeway at 30 miles per hour and accelerates uniformly to 60 miles per hour. From the odometer in the car, the motorist knows that she traveled 550 feet while accelerating. We want to determine A, what the acceleration of the car is, and we want to determine B, the time required to reach 60 miles per hour. So in this problem, we have some car. Let's draw a car. And we know our initial velocity is equal to 30 miles per hour. Now, we don't usually use miles per hour. We'll be using feet per second, so we will need to do that conversion. We know that we travel some distance. So at this point right here, we're going to call this x. Let me just make it a little clearer. So at this point right here, we're going to say that this is x is equal to 0. We're going to go some distance. And at this distance, we're going to say this is 550 feet. And right now, we know we need to do that conversion because we're in feet and we're in miles. So we'll have to do that conversion. And we know at this point, this final velocity is going to be equal to 60 miles per hour. We want to figure out what the acceleration is and what the time is. So we don't know what our acceleration is, but we know it's going to be positive because we're getting faster. And we don't know this time, so we don't know how long this will take. So when we go back and we look at the equations we have, and I'm just going to write them right here. So our initial velocity is equal, our velocity is equal to our initial velocity plus acceleration times time. Our position is equal to our initial position plus our initial velocity times time plus 1/2 times our acceleration times time squared. And our final velocity, for consistency, I'm just going to keep that as a v. So our final velocity is equal to our initial velocity squared plus 2 times a of x minus our initial position. So when we're looking at these equations, we need to pick equations. First, is this valid? It is valid because we're told that we accelerate uniformly. Because we accelerate uniformly, acceleration is constant. What you want to look for in these problems, we accelerate uniformly, or the acceleration is just some number, or you're under gravity. Gravity is another thing that you want to look for, since the acceleration due to gravity is constant. Or you could be told that it accelerates constantly. So since we accelerate uniformly, we know that these equations are valid for us. And because we don't have a time, but we have a final position. This time right here, these equations really aren't helpful because they require a time, and a time. So the only equation we can use to find our acceleration is going to be this last equation, or equation 3. And again, that's because right here we would need a time and we need an acceleration, a time and acceleration. So we'd have one equation and we would have two unknowns. You want to look for the equation to use which you'll only have one unknown. So in this case, we know what our final velocity is. We know what our initial velocity is. We don't know what our acceleration is, so that's what we're going to be solving for. And we know our location and our final and start location. So first, let's convert our miles per hour to feet per second. So our initial velocity is 30 miles per hour. We want feet per second. So we want to multiply first to get rid of our miles. So 1 mile. Let me move this down just to give myself a little bit more room here. So 1 mile is 5,280 feet. And then 1 hour is going to be 3,600 seconds. So let's go over to the calculator. And with the calculator, we're just going to plug this in. So we're just going to multiply 30 times 5,280. And we're going to divide that by, lost it. And we're going to divide that by 3,600. So we get this is equal to 44 feet per second. And we're going to do the same thing with our final velocity. So our final velocity, instead of 30 miles per hour, we're going to have 60 miles per hour. We're going to do the same conversion. 5,280 feet is 1 mile. And 1 hour is equal to 3,600 seconds. And the question I sometimes would get from students is, how do I know, like, if it's 1 mile on the top or the bottom? And the answer is, you can sort of treat these, you can treat these units like you would do a variable. So we know 1 mile is 5,000. 1 mile is 5,280 feet. So we can write it like that. So if we say 1 mile is 5,280 feet, that's just a ratio. It doesn't matter which way that we write it, but in terms of our equation, it does. And if we treat it like, if we treat our units like variables, we just want to make sure that our miles cancel out. Here, our hours cancel out. So what we're left with is feet per second. If the units were switched, I mean, it would be a ridiculous unit, but if we were in hours per mile, then our units would get switched, so they would still cancel out. So now we have one we know what our initial velocity is. We know what our final velocity is in feet per second. We know the equation that we're going to use. So what we're going to do is we're going to say that A, we're going to have our final velocity. Well, actually, we didn't calculate that. If we do calculate that, we'll get that this is equal to, it's going to be double. So it's going to be 88, but we can prove that. 5,280 divided by 3,600. So we sort of knew it was 88 because the velocity was just doubled. So our initial velocity is going to be this 88 squared. That's our final velocity. Our initial velocity is going to be this 44 squared plus 2 times our acceleration. We don't know our acceleration. And we're going to multiply it by our final position, which is 550 feet, minus our initial position, which we said is 0 feet. So when we do this, we're going to solve for acceleration. We're going to get that, let's see, let's simplify a little bit. We're going to get 88 squared minus 44 squared. So 2a times 550 is equal to 5,808. So then we're just going to divide by 2. We're going to divide by 50. And we get that my acceleration is 5.28. And this is feet per second squared. And if I was just a little more careful with everything, we could prove that in terms of units. So we know that this unit right here is feet per second. This is a feet per second, and this is a foot. So we have right here, we know that acceleration is feet per second squared. And when we multiply it by a foot, so we have a foot per second squared is equal to a foot per second squared is equal to, not is equal to, plus 2 times acceleration times a foot. So we'll have a foot squared over a second squared. These combine. These are like, so they just combine. And then when they combine, we divide by a foot, right? So that foot gets divided, and we're left with a foot per second squared. So we know that my acceleration is 5.28 feet per second squared. This is a positive 5.28, which that means my acceleration is increasing. So finally, we want to do B. And with B, we want to figure out the time required to reach 60 miles per hour. And we know now that 60 miles per hour is 88 feet per second. Okay, so now we want to, we know what our acceleration is. So we know that our acceleration right here, it's not a question mark anymore. It's 5.28 feet per second squared. So really, we could choose either of these equations, right? We know our initial velocity, we know our final velocity, we know our acceleration, we can solve for time, and we also know our initial, we know our final positions. Now, in general, you want to pick the easiest equation that you can pick. This has a squared term on it, so in order to solve it, you need to use a quadratic formula, most likely. So that's not typically the equation that you want to use. When you can solve this directly. So to solve it directly, we'll have our velocity, and our velocity is 88 is equal to our initial velocity, which is 44, plus what's my acceleration? My acceleration is this 5.28 times time. Now I can just solve this equation for time. And when I solve this equation for time, I'll have 88 minus 44 divided by 5.28. And I get that it takes me 8.3 seconds to start at 30 miles per hour, accelerate to 60 miles per hour in 550 feet. So this was a relatively straightforward problem that you might have. It's a single particle. It uses the kinematic equations because the acceleration is uniform, and this is how you would go about solving that problem. So let's look at a second example. And in this problem, we have a stone is thrown upward from a point on a bridge located 40 meters above the water. Knowing that it strikes the water 4 seconds after release, we want to determine the speed in which the stone was thrown upward and the speed with which the stone strikes the water. So on problems like this, there's a few things. Is the acceleration constant? Oops, 1 second. Is the acceleration constant? Yes, the acceleration is constant because when we throw the stone up into the air and it falls back down, the only force that acts on the stone is gravity, and gravity is constant. So if you're in free fall, acceleration is constant. So let me put that right here. Free fall. Oops. Free fall is constant acceleration. The other weird thing about this problem is when we say we throw a stone straight up into the air, we mean we throw a stone straight up into the air. So the stone goes straight up into the air and it comes back straight down. There's no parabolic motion to it. We're not throwing it. So drawing it is sort of a problem, but it does not go up like this and come down like this. It just doesn't do that. Even though I may draw it just for clarity, like, okay, it goes up and down, understand that there is no change in this x distance right here. It's just we're in rectilinear motion in one direction. So in this case, we're only dealing with the y direction. So let's draw this problem. So we have a stone is thrown upward from a point on a bridge located 40 meters above the water. Okay, so let's do it like this. Here's the bridge. We have water that's below it. This position is going to be 0 meters, I think we're in, right? Yeah, 0 meters. This position is going to be 40 meters. Okay. I'm going to define upward to be my positive y direction, and this is important. Up is my positive y direction. I could have defined down to be positive y. But then my signs would have to change on my 0 and 40. This would be 0 and this would be 40. But if I define y to be positive up, gravity always acts downward. So since gravity is acting downward, gravity is going to be equal to minus 9.81 meters per second squared. So again, we throw it upward. So it has an initial velocity. We don't know what our initial velocity is. We're trying to find that, the speed in which the stone was thrown upward. So we throw it upward with some initial velocity. And then let me move these over. And then it's going to come back down. Remember, it doesn't move. So I'm just drawing it offset because we need to visualize it, but it's actually straight up and down. And this final velocity right here is also unknown. Now, the thing about final velocities, I know a lot of times what people want to do is say, oh, it hits the water. Its final velocity is equal to 0. No, the final velocity is equal to 0 in a projectile problem or a problem like this because after it hits, the forces stop it. We're saying that this is going to be the velocity, the instantaneous millisecond, before it hits the ground. So it's none of the forces are acting on it at all. So that's what we mean by its final velocity. Yes, if we extend the time into, we know it's 4 seconds, into 6, 7, 8 seconds, yeah, its velocity is eventually going to stop. But at 3 seconds, it's right before it hits the water. The millisecond before it hits the water, what is its velocity? All right, so let's list out the equations that we have. We have that our velocity is equal to our initial velocity plus acceleration times time. Our position is equal to our initial position plus our initial velocity times time plus 1/2 our acceleration times time squared. And our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our final position minus our initial position. Okay, so what do we do now? Well, we look for, if we're looking for the speed in which the stone was thrown upward, we know that we have constant acceleration. Which of these equations have the least number of unknowns? Well, we want to go with this second equation right here. If we go with our second equation, we know our final position. Our final position is 0 meters. Our initial position is 40 meters. Our initial velocity is unknown. Our time is, I didn't draw this, but we know that our time is 4 seconds. And our acceleration is gravity. So let's plug in everything that we know. So for A, we have x, 0, is equal to our initial position, 40, minus our initial velocity, that's what we're solving for, times 4, plus, this is a plus, plus 1/2 times my acceleration, which is minus 9.81, times 4 squared. All right, so let's put this in the calculator, and what we'll get, we need to solve for this this v naught. So really, right, this comes to the other side. So minus 4 v naught is equal to 40 plus 1/2 times minus 9.81 times 4 squared. So we'll have 40 plus 1/2 times minus 9.81 times 4 squared. And we're going to divide this by minus 4. And we get my initial velocity is 9.62, and this is in meters, so meters per second. All right, so now we know our initial velocity. We know how far that we throw, how fast we throw this stone upward into the air. So now we want to figure out the speed at which the stone strikes the water. And really, we could use either of these two equations. We could use this one, or we could use this one. We know everything except our final velocity. When you have a choice, this is, again, probably the easier equation you have to work with. If you decide to work with this one, you have to interpret it just a little bit more. So we'll work through it that way in a minute, but let's go through using our first equation. So we'll have that our final velocity v is equal to v naught. So that's going to be this 9.62. We know it's going upward, so we know it's positive. It's in this positive y direction. So 9.62 plus my acceleration, which is this minus 9.81 times time, which is 4. So 9.62 plus minus 9.81 times 4. And we get that my velocity is going to be equal to minus 29.6 meters per second. The negative sign makes sense. The negative sign says we're going in this direction. Because I said anything that's going upward is positive. Because I have a negative sign, it means my velocity must be pointing down, which sort of makes sense. When you think about the problem, the stone's falling downward. Now, what happens if you decided to use this second equation right here? So if you decided to use this second equation and you said v squared is equal to my initial velocity squared, so 9.62 squared plus 2 times minus 9.81 times x minus x naught. So x is my final position, which is 0. X naught is my initial position, which is that 40. So we'll have that v squared is equal to, let's get this number right here, 9.62 squared plus 2 times minus 9.81 times minus 40. So you get this velocity is equal to 877.34. And now we have to take square root. So when we take the square root, we get the square root of this number. Oops. The square root of this number is going to be equal to 29.62. Well, what happened? In this case, we solved directly and we got this minus sign. In this case, we don't have that minus sign. But you have to remember when you're taking the square root, what you're really getting is this is going to be equal to plus or minus 29.62. And you have to use the context of the problem to know that we are moving down, right? We are moving down because the stone is falling. So we have to choose this negative value of the square root. So again, this one is just a little less direct. When you have a choice, always try to use the more simple problem. All right. So let me get to the next problem I want to go over. So we've done 2 problems of single particles using the kinematic equations. I want to do another problem where we have multiple particles. When you have multiple particles, what you need to do is you need to figure out some part of the question where they're tied together. So it's going to typically be at some time they're at something happens, or at some position they're equal. And in this case, we're going to start by saying, all right, here's boat A. Boat A is ahead of boat B by 50 meters, and both boats are traveling at a constant speed of 180 kilometers per hour. We know we're going to have to make this meters per second. At time equals 0, the boats accelerate at constant rates. They accelerate at constant rates. That means acceleration is constant. That means our kinematic equations are valid. Knowing that boat B, passes boat A when time is equal to 8 seconds and the velocity of A is 225 kilometers per hour, we want to determine the acceleration of boat A, and we want to determine the acceleration of boat B. All right, so let's draw this out. So at time is equal to 0, we have boat A over here. Actually, I don't want to go up and down. I want to keep it in the x direction. So we'll say that boat A is over here. And boat B is over here. So this, boat A is ahead of boat B by 50 meters. So right here, this is 0 meters. Right here, we're going to say this is 50 meters. Anything that's going in this direction is going to be positive. And let me line this up just a little bit better. Okay. So then we know at time is equal to 8 seconds, we know that the positions are the same, right? At that point, B passes A, which means that it has overtaken the position. But we're saying at that very split instantaneous second that the positions are the same. So we're going to have B, and we're going to have A. So let's first figure out what we need to do in this problem is we need to keep track of each of these boats individually. And then we know at that time, the positions of both these boats are going to be at the same place. But let's figure out what 180 kilometers per hour is in meters per second. So velocity, my initial velocity of A is equal to the initial velocity of B, which is equal to 180 kilometers per hour. And we need meters per second. So let me do it like this. We know that 1 kilometer is 1,000 meters. We know that 1 hour is 3,600 seconds. So we know that 180 kilometers per second, we're going to multiply by 1,000. We're going to divide by 3,600. And that's equal to 50. Okay, so then we know that the final velocity A, it's equal to 225 kilometers per hour. Again, we're going to do the same thing. We're going to multiply it by 1,000. Meters is 1 kilometer, and we're going to say 1 hour is 3,600 seconds. So 225 times 1,000 divided by 3,600 is 62.5. and this is meters per second. Okay, so now we know our initial velocities and our final velocity of A. We don't know what our final velocity of B is, but that might be okay. So let's look at what the acceleration of boat A is. Again, we have to keep boat A and boat B, the accelerations, the velocities separate. So what we're trying to do for A, we're trying to figure out our acceleration of boat A. Let me draw or write out my equations. So velocity is initial velocity plus A times t. My position is my initial position plus v naught t plus 1/2 at squared. And my velocity squared is equal to my initial velocity squared plus 2 times the acceleration times x minus my initial position. So if I'm looking at boat A, what do I know? I'm looking for its acceleration. I know its initial and its final velocities. And I know how long this takes. I know this takes 8 seconds. So I can use this equation right here to solve for what my acceleration of boat A is. So I can say that my velocity of A, let me write the velocity of A is equal to the initial velocity of A plus the acceleration of A times the time. And the time of A and the time of B are the same, right? Because they're in the same reference frame. Everything that happens at time 0 and time 8 is the same for both of those. So we're just going to call that t. So my velocity of A, my final velocity is 62.5, is equal to my initial velocity, which is 50, plus my acceleration of A times t. Times t, which is 8. Okay, so we'll do 62.5 minus 50 divided by 8. And we get my acceleration of A is 1.56 meters per second squared. So that's what my acceleration of A is. So now I need to figure out the acceleration of boat B. How do I do that? Well, there's a few things that I know. I know that everything happens at 8 seconds. And I know that because B overtakes A, the position of B is going to be equal to the position of A. And these are its final positions, right? This is the initial position of A. This is the initial position of B. But I know at 8 seconds, the x of A, x at of boat B is equal to x of boat A. The positions are the same. So what can I do? Maybe the first thing I should do is figure out where boat A is. So I'll say x A is equal to my initial x of A plus v naught of A times time plus 1/2 times the acceleration of A times time squared. Okay, I'm looking for this. I know my initial position is 50. I know my initial velocity is 50 meters per second. My time is 8 seconds. And my acceleration I just found is going to be 1.56. My time is 8 seconds. So I can put that into the equation, 50 plus 50 times 8 plus 0.5 times 1.56 times 8 squared. So I know my final position is 449.9. I'll call that 500 meters. Okay. So I know this is equal to x of A, my final position of A. This is also equal to x of B, my final position of B. So now what can I do? All right. If I use this equation again, but instead of x of A, I use x of B, I know my final position of B. I know my initial position of B. I know my initial velocity of B. I know my time. The only thing I'd have to resolve this to figure out, okay, what is my acceleration of B? So let's do that. So I have x of B is my initial position of B plus my initial velocity of B times time plus 1/2 times my acceleration of B times time squared. Okay, I know this. I know that this is now 500. I know that this is equal to 0. I know my initial velocity of B is 50. Time is 8. And then 1/2. The acceleration of B is what I'm solving for. And then I have my time 8 squared. Okay, so we'll go 500. We'll say, all right, minus 50 times 8. It's 100. We'll multiply by 2. And we'll divide by 8 squared. And I get that my acceleration of B is equal to 3.125 meters per second. Does this make sense? It does. The acceleration of B is faster than the acceleration of A. It makes sense with the problem because my boat B is going to overtake boat A, so it should have a faster acceleration. And this is how you do problems involving multiple particles. You find something, and there always will be something that will be the same, whether it's the same time or whether it's the same position. Those are typically the two that you'll see, but maybe the velocities are the same. And you have to keep the equations separate, but something will tie them together in these problems. All right. So the next thing I want to do is I want to talk about more motions of several particles, but I want to talk about relative motion and pulleys. And really, relative motion and pulleys, well, pulleys in general, when I was a student, I really disliked them. But then as I started to teach this class, I really started to enjoy pulleys and enjoy pulley problems. So I spend a lot of time when I'm teaching this class in person on pulleys. But first, I want to talk about relative motion. And relative motion is sort of important when we get to pulleys. But what relative motion is if I have some, we'll do velocity, but this can work for velocity or position. Well, we'll start with position. If I have some position that's B with respect to A, the equation that I'm going to use is going to be x of B minus x of A. I find it easier to understand in terms of velocities. So my velocities, if I differentiate this equation, I get my velocity of B with respect to A is equal to my velocity of B minus my velocity of A. I can do the same with acceleration. I can say that my acceleration of B with respect to A is equal to the acceleration of B minus the acceleration of A. Again, I find it most intuitive to work with velocities because with velocities, you can sort of think of it in terms of cars and driving on a highway. So let's look at the velocity, but understand that it works for the position and the acceleration. If I'm standing on the side of the road and I'm not moving, so I'm going to be particle A. My velocity of A is equal to 0. And there's a car that's going past me. And this car, well, let me not draw it in what looks like 2 dimensions. Let me draw it going straight up. The car is going, say, at 50 miles per hour. So this is particle B. Its velocity is 50 miles per hour. When we want to figure out relative velocities, right, it depends on the reference frame that you're looking for. If I'm the reference frame, my velocity is 0. So the velocity of B, the velocity of the car with respect to me, is going to be its velocity 50 minus my velocity, which is 0. So to me, the car looks like it's moving at 50 miles per hour. And this is the velocity of the car, B, with respect to A. Now, let's say I'm not stationary. Let's say that I'm also in a car and I'm moving at, say, 30 miles per hour. And the other car is still moving at 50 miles per hour. So this is B, I'm A. We're going to do the same thing. We're going to say the velocity of B with respect to A. So the velocity of B with respect to A is the velocity of B, and we said this is 50. So B minus 30 is going to be equal to 20 miles per hour. And we're assuming that the acceleration is constant in this particular case, and that sort of makes sense with what we've experienced. If we're moving at 30 miles per hour, and the car that is passing us at 50 miles per hour relative to us, the car only looks like it's moving at 20 miles per hour. But we can flip this around. So we can also say the velocity of A, us, with respect to the car, all we'd have to do is flip around the variables. So when you look at this equation, it's this formula that you have. So if you have B with respect to A, it's going to be B minus A. If you have A with respect to B, it's going to be VA minus VB. Okay, so now this is saying that the velocity of us with respect to the car that's passing us, so the reference frame is the car that's passing us. Okay, this is going to be 30 minus 50, and this is going to be equal to minus 20. And again, that makes sense. If you're the car that's passing us, we look like we're going backwards at minus 20 miles per hour. So that's how relative motion works. And again, it's going to be the same for the relative motion, relative velocity, and relative acceleration. But to me, the relative velocity is easier to get a handle on. Okay, so we have relative motion, but what do we do with pulleys? So with pulleys, these are some sort of particles that are interconnected. So they're dependent motion. So I'm going to have a very simple example of a pulley. And hopefully, intuitively, it will make sense. So I have a pulley on an inclined plane. I'm going to call this block A, this block B, and this pulley is going to be connected with a rope. Intuitively, I know that if I move some position A this way, B has to move this way. If I move, they're connected, so if I move with some velocity, B has to move with the equal and opposite velocity, right? If this goes this way, this must go this way. Okay, so there's a couple of assumptions we need to make with pulleys. One, with pulleys, pulleys are massless. Two, pulleys do not stretch. The rope of the pulley does not stretch. The length of the cord is completely constant. So pulley is not the right word, but the rope or cord does not stretch. So we can neglect any mass of the pulley, and we can neglect any elongation of the cord. So when we're doing this problem, for step one, we have to establish coordinates. So we establish position coordinates, and these position coordinates need to be from a fixed location. In this case, when we look at this, we have a pulley which is mounted on this incline. So the pulley is fixed. So what we want to do is step two. So we want to dimension in this particular problem. We want to dimension everything from this pulley because that is the only fixed point that we have. So coordinates are directed along the path of motion and extend to a point having the same motion as each particle. So point 3 is that the origins do not have to be the same for each coordinate. And I'm going to explain how we do 1, 2, and 3 in a minute. Okay. What this means is we pick a fixed point. We want to dimension everything that moves in a single direction from that fixed point. So that means I have this particle that's moving in this direction. I have this particle that's moving in this direction. So from my fixed point, I want to define this line right here. And this line is going to be this positive direction. Let me get rid of this. Get rid of this. From this line, I want to define this length right here, and this is going to be the positive direction. So now what I want to do is I want to add up the total length of pulley. So we're going to extend from our datum point right here. Let me keep it two different colors, but we're going to extend from our datum point, and let me clean up my datum points. So this and this. So if we extend from our datum point, we're going to call whatever this length is right here. In terms of notation, I've seen it used as S or I've seen it used as L. I'm going to use it in this case as L. So this is my length of A. That distance right here is a position of the pulley that as this block goes up and down is going to change. It's going to vary. So my total length is going to be this length of A. And then we're going to have whatever this length is over the pulley. And we're just going to call this some constant length. Regardless of where blocks A and B are, this length that goes over the pulley is not going to change. If it's 1 meter, or a half meter, it's always going to be 1/2 meter. So then we're going to have plus L constant. Then we're going to go this way. So this is L of A. And typically how I like to do this is I like to draw an arrow like this. And I say this is LA, that's LC. And this right here is LB. Let me use a different color. So this is LB. So what I've done is I have figured out the total length of this rope. This rope is the total length. We can say the total length is equal to this length of A plus this length over the pulley plus this length of B. So now, that was step 4. We want to use geometry or trig. Let me get rid of this for a minute. To relate coordinates to the total length or portion of cord that we're looking for. Of string. There's a step 5. That's sort of a starred step 5. If we have multiple chords, and I don't have any problems tonight that have multiple chords, but if multiple chords each chord needs their own equation. So I'll do a multiple chord problem next time. I didn't even get one this time. But what we can do is at this point, we can say, all right, okay, let's differentiate our position with respect to time. And when we differentiate our position with respect to time, we're going to get our velocity. So when we, this is the total length. So the thing is, when we differentiate the length, the total length is a constant value, right? Over time, the total length is never going to change because it does not stretch. So when we differentiate the total length, we get this is equal to 0. When we differentiate our length of A, the length of A is variable, right? If the box is moving up, it's going to get shorter. If it's moving down, it's going to get longer. So this is going to be some velocity. The length of cord that's over the pulley is never changing, so this is also 0. And the length of cord that's over for part B is also going to be changing. If B moves up, it's going to get shorter. If B moves up right here, it's going to get shorter. If B moves down like this, it's going to get longer. So we know that B is going to have some velocity to it. So pretty much when you take the derivative with respect to time, if the position can change, it becomes a velocity. If it can't change, it becomes 0. So we get 0 is equal to VA plus VB. And that shows us everything we need. We get that the velocity of A is equal to minus the velocity of B, right? If we have to go from our positive points right here, we know that if A is going this way and we have a positive velocity, we know that B must be going this way. And that means we have to have a negative velocity because we're going opposite our positive direction. So that's what this is telling us. We can take it one step further. And if we go one step further, we get the acceleration of A is equal to minus the acceleration of B. But again, that's just another derivative. And the biggest step and the most important step. This is usually the hardest to find, the total length, and then just remembering when you differentiate, anything that's constant becomes 0. Anything that is variable will become velocity. Going from velocity to acceleration, any of your velocities are automatically going to turn into accelerations. So hopefully that helps a little bit. So really, we want to do problems with these pulleys. And with this one, this is a very simple pulley problem. We want to calculate the relationship between the velocity and acceleration of points A and B. And there are no numbers to this. So this one, all we're trying to do is work it without numbers, just like we did in the last problem. So step 1, we have to find our fixed point. When we look at this pulley problem, the reason pulley problems are difficult is you have to imagine what happens when you pull on the pulley. And we have to use our intuition to know, well, if I pull pulley B down, then that means pulley A is going to have to go to the right. Sometimes it's really difficult to see what's going on with these pulleys, but you have to see what points are going to move. So if I move B down, A is going to move. So where's my fixed points? Well, A has a fixed point. It has this pulley. I should have drawn it like this. Right, this pulley is fixed on the ground. And then this pulley right here is also fixed to the top. So what I want to do, I want to dimension my datum line for my y direction to go through this pulley right here. And then I want to dimension my datum line for anything going to, right, so this is positive in this direction. Then I want to dimension, well, let me take a step back. By dimensioning this, I can dimension any vertical line. But I can't dimension this line that A is at because it's going in the horizontal direction. So I need another line that is going to go through A, and I'm going to define my positive direction this way. We always define the positive direction. We never define a negative direction. So now I want to figure out the total length. And after you get comfortable with these pulley problems, when you're figuring out the total length, you can sort of ignore the constant, the small constant lengths like what's going over a pulley. But right now, since we're still working through how to do these problems, I'm going to account for every length of the pulley. So right here, this length right here is never changing. So I'm going to call my total length is going to be equal to, I'm going to call this constant 1. So it's going to be equal to constant 1. Then what I like to do is I like to put a dotted line through everything that I need to dimension to. So I'm going to have an arrow. And this arrow goes from my datum to the pulley. And I'm going to call this length of B. So now I go down and I get a length of B. As I follow my pulley, I have to go around the pulley. And that length, again, it's going around a pulley. It's never changing, but I'm going to call that plus, we'll call this C2. C2 seems like a good idea right now. So this is C2. Okay, now I come back up, and this distance right here is also LB. So this is going to be plus LB. Now I'm going to go back around this pulley. I'm going to call this C3. So plus C3. And I'm going to now go down right here. All right. Now, this is a tricky one. This is never changing. This length right here is actually between two fixed points, right? It's between this pulley point and it's between this pulley point. So we're just going to call that C4. And that's how pulley problems can be a little bit difficult. If you didn't see that was a fixed distance, most likely the problem's going to you're going to get the problem wrong. So we're going to call that C4. Then I didn't really draw it, but we'd probably have some little bit of rope that's going over this pulley right here. Call that C5. I'm just using C for constant. And then we go down this rope right here. Well, this rope, this distance is variable. I'm going to call this LA. So we're going to say this is plus LA. When we differentiate, so that's the total length of this rope, right? Constant plus a LB, constant plus we go up LB. Now, a mistake I've seen, I just want to point this out, is we're always adding the lengths. Sometimes what I see is, all right, we start on this end of the rope, we go down and we call this LB. Then we go around and we call this, well, I'm going back up, so I'm going to subtract LB. We don't want to do that. We just want to be adding lengths of the rope because we want to get the total length of the rope. So don't subtract lengths of the rope when you're accounting for it. Sometimes I just don't subtract the lengths of the rope. So now what we have to do is we have to differentiate. When we differentiate to get our velocity, well, our total length doesn't change. Constant doesn't change. This does change. It's a length, so it's a velocity of b. Constant doesn't change. Well, now we have a velocity of b. Constant doesn't change. Constant doesn't change. Constant doesn't change. And now we have a velocity of a. Really, when you get used to these problems, you're not going to spend the time to add up all the distances over a pulley. So like C1, C2, C3, and C5, you're just not going to account for them because you're just going to know that the length of the rope is not changing over them. But what we can say, if we combine our terms, is 0 is equal to 2 VB, which plus VA, and we get my velocity of A is equal to minus 2 times VB. All right, that's all that is to a problem like that. If we wanted to relate the accelerations, we take another derivative. So we'll get that the acceleration of A is equal to minus 2 times the acceleration of B. Going from velocity to acceleration is very easy. Again, the most difficult part of these problems is actually figuring out the total length of ropes. Okay,